Hi everyone, I'm Tawalari, a third year PhD student of Mechanical Engineering, Stony Brook University. I'm also a full member of Sigma X. Today I'll be presenting my research progress, which I titled From Contrail Modeling to TPMS heat exchangers. My research contributions towards advances in aviation, energy, and environmental sustainability. The motivation for my research has been my advisor in person of Professor Folucio Ladende. He has been working on this for more than 3 decades, graduated many graduate students, and his goal is to be able to develop a supersonic commercial airliner that could fly from United States to Korea under 1 hour, producing limited effects on climate. So I started with this goal, studying the effect of air vehicles on climate. Then I progressed to study rotating rotation engines, and I'm currently studying triply periodic minimal surface heat exchangers. So contrails are forcible line from ice formed behind aircraft flying in the stratosphere. It is formed as a result of low ambient temperature and high relative humidity, supporting condensation of water vapor from the ambient or from either the ambient or the jet exhaust on the soot particles in the jet plume. Contrails will continue to grow or persist to form artificial cloud if the temperature of the ambient is below 232 Kelvin. Yes, it will disappear. The persistence of contrail or continuous growth of contrails will lead to artificial cloud, which increase the number of cloud in the atmosphere, absorbing heat from the sun and releasing heat in the evening, increasing global warming. So the motivation of studying contrail computationally is because contrail formation or studying of contrail is mostly being done experimentally using traditional method of in-source measurement. But because contrail is a global measurement, there are errors, which errors due to approximation of. So it is better to study contrail, which is divided into regimes, the jet regimes, the diffusion regimes, and the dissipation regimes in between, to study them computationally. Little has been done in this area, especially at the jet regime of contrail. This is why I want to study this. And my objectives are to study the contrail formation at the jet regime, a regime which contrail is formed, and to study contrail persistency, what causes this to persistent, how does it persistent, apart from the effect of temperature with ambient temperature that we know that causes persistence, which other effects or quantities causes persistences of contrail, and to study the interaction of contrails and the atmosphere. Also, finally, to study the effect of contrails on climate. So I'll be using a approach. I'll use a physics-based approach to start to model the jet exhaust and ambient, to plumb the ambient, then applying LES to solve Navier-Stokes equations, methods in solving Navier-Stokes equations, and using Lagrange particle tracking to track ice particle. Unfortunately, I won't be presenting my results here because my results are submitted under publication. They are all under publication. So next, I move to the study of detonation by doing a comparative analysis of induction zone dynamic across multiple fuel in detonation, rotating detonation engines. So for everyone to understand detonation better or rotating detonation engines better, so I shall avoid flames and combustion. Basic combustion, flames is chemical zone of combustion. Flame is the chemical zone of combustion. So we have two types of flames. We have the premise flames and the diffuse flame. There are there are many flames in between, but primarily we have premise flames and diffuse flame. So the premise flame is the oxidizer and the fuel has been premixed before combustion took place, but the diffusion place means the fluid diffuse into the oxidizer as shown in the figures in the figure 1. By your left you have the premixed flame, and by your right you have the diffuse flame. But in our in our business, we deal most with the premixed flame, which can either be deflagration or detonation depending on the speed of the combustion wave. If the speed of the combustion wave is supersonic, then we have detonations. If the speed of the combustion wave is subsonic, then we have deflagration. Supersonic is compulsory to get a supersonic combustion, which also means to fly supersonically, you have to have detonation. So yeah, the parameter of detonations, comparing this table 1 compared detonation and deflagration. The Mach number of detonation is between Mach 5 to Mach 10, and the Mach number of deflagration is between exponential is between to the exponent of 1 to exponent of minus 3. Yeah. So then in detonation engine, we have actually two types of detonation engine. We have the pulse detonation engine and the rotating detonation engine. As the pulse implies it's stationary, while the rotating implies it's rotating. So rotating detonation engines has a rotating combustion chamber. First of all, that will make it. The combustion chamber is like an angular ring where air fuel is injected from the bottom. Based on its air from the upstream, fuel is injected to the downstream, goes straight to the downstream, and detonation wave occur. Detonation wave, which is the wave which moves supersonically above Mach 1. Yeah, above Mach 1 or close to Mach 1. So of course, supersonic detonation engine offer high power efficiency and a hypersonic combustion. Hypersonic in the essence in the term of from 0.8 to 5 and above Mach number. Oh, I have to pause on that. Well, while most while most of the while most of the studies on detonation waves uses hydrogen as fuel, my goal is to use some heavy hydrocarbon, some light hydrocarbon fuels such as methane, ethylene, and some JP fuels like kerosene. Likewise, some eco-friendly fuel like ammonia. To understand the induction zone behavior across the different fuel of the rotating detonation engine performances. So these are my objectives: to understand the behavior of rotating, in particular focusing on the induction zone, to validate fuel behavior comparing for traditional wide detonation tube setup, and to perform a 2D simulation. Also compare my result of 1D of hydrogen to methane, hydrogen, or other mixtures such as ethylene, in the future JPs and ammonia. So for the simulation setup, a 1D detonation engine actually an open toe chamber of a 10 centimeter in length and about 0.1%, 0.1 centimeter was used as the hotspot zone for ignition of the mixture, and no slip boundary condition was used. We used Musk and Wano engine for the partial scheme and beam warming engine for the temporal scheme. So we use different kind of mechanism, 2-step 4 species, all the way to 19-step 12 species. So this was done for methane and hydrogen fuel, and we compare our results for methane using from the pressure distribution from the upstream to the downstream for both methane and hydrogen. You see, and you can see the hydrogen combusts faster, about faster, about 1 centimeter to the downstream, while methane combusts slower, very slow to combust. So in principle, people often mix methane with other fuels to achieve combustion, but in this case, I use pure methane. So I'm also presenting result of comparing the temperature and pressure for both methane and hydrogen. The same. We see hydrogen shows as expected a good result as expected, while pure methane shows a little not good enough result. So we say this species moving up from from the upstream to the downstream, the combustion actually takes place faster in hydrogen compared to pure methane. So then I'm working on sandwich panel triple periodic minimal surfaces heat exchanger. The goal is able to take heat from aircraft to control aircraft cooling system, and the principle is taking heat from an aircraft engine can make it fly supersonically, removing excess heat transfer. So triplet periodic surface giving us a surfaces that can a large surface area can help us dissipate heat to its volume ratio. So triple periodic minimal surfaces are mathematically defined continuous and periodic structures with minimum surfaces and no self-interaction. They are widely used in engineering and material science for creating a lightweight, high strength, and high surface area structure, which make it applicable in the case of heat exchanger because we need high surface area to increase its transfer rate or to dissipate it faster. So the goal is to use, and this is a sandwich panel heat exchanger, to have the layer first, the upper skin layer, the core, and the lower skin layer with some binder. So the core will be TPMS structure. It can be gyroid or so many types of TPMS, gyroid, diamonds, play, so many. But gyroid has been proven to be efficient, to have more efficiency in many cases of application. So in this case, I developed the core of the TPMS sandwich panel activities using and topology that are meshed with fidelity point-wise. Then for modeling or running simulation on it, I have to create a unit cell, simulate a unit out of my TPMS structure. So the process is now modeling with tip and topology, generating the mesh with flank meshing, and simulating it with axis flame. So I use a unit cell. I take a unit cell out from the TPMS structure, then I simulate it, and these are my results. So these are the boundary conditions for the cold fluid inlet and then hot fluid inlet. The velocity is 5 meters per second. Velocity is 5 meters per second and 1 meter per second respectively. And the temperature is 283 Kelvin and 553 Kelvin respectively. So at the outlet, I achieved the same temperature of 300 Kelvin for both cold and hot fluids. So these are my temperature contour plot results, showing my result. On the summary is I was able to develop physics-based high evolution simulation to model aircraft exhaust form of to study the formation of contrails at the jet regime and the persistences of contrail. Also, likewise, in the rotating simulation engine, a 1D induction zone of rotating denotation engine was for hydrogen fuel and methane fuel has been studied on. We're currently working on ethane and JP10 fuels. And likewise, I'm working currently on TPMS heat exchanger using a soldering panel TPMS heat exchanger, so to make the base of an aircraft to be an heat exchanger, removing heat from the engine and cooling the fuselage so that the aircraft could fly supersonically. Thank you for your time.